My name is Monte. I'm an assistant professor of geography here at CU Boulder. It's my pleasure to introduce Dr. Stephen Quiring of the Atmospheric Science Program, Department of Geography of The Ohio State University. We have a very exciting talk titled Modeling Weather Risks, Applying Analytics to Inform Electrical Utilities. Dr. Stephen Quiring is a professor in the Atmospheric Science Program at the Department of Geography at Ohio State University. He's a fellow at the Risk Institute at the Ohio State University Fisher College of Business and a member of the Translational Data Analytics Institute and the Sustainability Institute at the Ohio State University. Prior to his arrival at Ohio State, Dr. Quiring spent 11 years at Texas A&M. His research focuses on hydroclimatology, weather data analytics, and modeling the impact of storms on electrical infrastructure. He has published more than 90 journal articles and has received more than $14 million in funding from federal agencies, including DOE, NSF, NOAA, and state agencies, including an NSF Career Award in 2010. Dr. Quiring is associate editor of the Physical Geography and the Journal of Applied Meteorology and Climatology. He received his BA in Geography from the University of Winnipeg in 1999, a Master's in Geography from the University of Manitoba in 2001, and a PhD in Climatology from the University of Delaware in 2005. Without further ado, I want to invite Dr. Quiring to present his talk on modeling weather risk, applying analytics to inform electrical utilities.
Good afternoon. Thanks, Morteza, for the invitation, and thanks for this opportunity to present to the CU Boulder community and all of those other folks who might be listening to this presentation. It's one of the unique opportunities that's provided by COVID. I guess we can take advantage of technology, and it really makes it easier to share these kinds of talks to kind of democratize or open them up to a broader range of people. And I've found that for myself, that's great. I can participate in seminar series that I haven't been able to before. So today I'm going to be focusing on looking at the impacts of storms, and in particular, we'll focus on hurricanes because we're in the hurricane season, and this week is the climatological peak in terms of activity in the North Atlantic Basin. And as was mentioned in the introduction, I spent the first part of my career at Texas A&M University. And in fact, I started at Texas A&M in 2005. And for those of you who are familiar with hurricanes, you'll remember that the 2005 hurricane season is a record-setting hurricane season in terms of the number of named storms, and also Hurricane Katrina, and a little bit later in the season, Hurricane Rita. And I was a faculty member in College Station when people were, after all of the damage and destruction wrought by Katrina, a short while later, evacuating in front of Rita, and in fact the places in College Station, which is pretty far removed from the coast, were boarded up. And so I'd like to, before I begin, just acknowledge all of the collaborators and the team of people. This is work that has spanned about 15 years, and so there are a large number of people who I need to acknowledge, the first of which is my primary collaborator, Dr. Seth Geikema, who's in the Industrial and Operations Engineering Department at the University of Michigan. And for those of you familiar with Big Ten football, yes, it is possible for OSU and Michigan to collaborate, at least in the research realm. There's lots of other people that I'd like to acknowledge, one of which is the research scientist who is primary on my research team for working with the utilities, and that's Dr. Brent McRoberts. So when it comes to why as a climatologist am I interested in this question, and how did I get involved in it? There are many major weather-related disasters that occur in the United States each year. And NOAA keeps track of this billion-dollar weather disaster record. And this clearly shows from 1980 through 2020 that the total number of billion-dollar weather disasters in the United States has been increasing. And if we look specifically at tropical cyclones and severe storms, that's the yellow and green portions on the bar graph here, shown on the left y-axis, the number of events, that there are many more, especially of the green, severe storms that cause more than $1 billion of damage since 2005 than there were prior to 2005. We'll also note that there's substantial interannual variability in tropical cyclones, especially those that make landfall in the United States and that result in billion-dollar weather disasters. But if you look at this red line superimposed on the counts of events, that's the total losses, estimated losses in billions of dollars. And you'll note three peaks in this graph, one in 2005, one in 2012, and one in 2017. And those three peaks are important because 2005, this peak is driven by Hurricane Katrina. The peak in 2012 is driven by Superstorm Sandy. And the peak in 2017 is driven by Harvey, Irma, and Maria. And so tropical cyclones have a major impact in terms of losses in the United States, and not just for the economy as a whole, but also when we think about impacts on the electrical power grid. So here as a climatologist, I'm interested in what we might call weather data analytics or applied climatology, using weather and climate information to inform decision-making and to enhance resilience in the face of climate variability and climate change. And if we look at major outage events as recorded in the DOE 417, based on the DOE 417 criteria, we can see about 83% of major disruptions to the power system, major outage events that occurred between 2003 and 2017 were associated with some type of storm. And not surprisingly, when we look at what some of the largest of those events were, and I already mentioned some of the more recent ones with Harvey and Irma and Maria, but we can also look earlier in the record and see that things like Katrina and Sandy and Ike show up here, causing millions of power outages and billions of dollars in economic losses. And so it's estimated that weather-related power disruptions, so now specifically focusing on the impact of loss of electrical power due to weather, is about a $20 billion per year hit to the US economy. So a significant and frequent occurrence. So what type of weather events cause the most problems? We can divide this, and we've done this based on that DOE data set that I mentioned on the previous slide, and look at events for the 2003 to 2017 period and identify how many events were thunderstorms, how many events were tropical storms or hurricanes, and how many events were winter storms. And you can see based on the right-hand side pie graph here that almost half of the events are thunderstorms. So thunderstorms are obviously the most frequent. They affect the largest number of locations within the United States. And that the smallest is actually tropical storms or hurricanes. These are the least frequent. But when we switch how we count this and now count up the total number of customers affected, that tropical storms and hurricanes cause the greatest number of customer impacts, even though they're relatively infrequent. Another way that we might want to think about this from a utility perspective is in terms of their costs or the outage duration. And so this is a unique data set that we were provided through a benchmark study run by First Quartile Consulting that surveys utilities on an annual basis and where they self-report their responses to major storm events. And so from this data set, we know things like the median amount of damage or losses that each utility reports. And so the green bars here represent thunderstorms, the orange represent our tropical cyclones or hurricanes, and our blue represents winter storms. So if we focus on costs in the lower left-hand corner here, we can see that the highest median cost is associated with tropical cyclones and hurricanes, and that thunderstorms and winter storms are typically a lot lower. Although for all of these, there's a tremendous range. So that's why we're using the whiskers here to represent the variation in the data. Another place of interest would be to look at restoration time. So this is after a major weather event occurs and people lose power and there's damage to the electrical system. How long does it take on average to complete the restoration? And again, we can see that tropical cyclones and hurricanes rank at the top of this list. And in some cases, the restorations are really, really long. And we'll mention one today that's still ongoing, from Hurricane Laura that recently impacted Louisiana. And so this restoration for one utility serving the state of Louisiana, Entergy, is entering its third week, and they still have a lot of work left to do. So there's something like 60,000 customers still out from Hurricane Laura today. So that, if we included that one in our graph, it would be way off the top of the chart here. Another aspect to look at is how many people are required to complete the restoration. So most utilities do not have enough crews in-house. They don't have enough regular employees of their company to handle all of the restoration on their own. Therefore, they need to rely on others, mutual aid agreements. So they borrow employees from other sources and from contractors to do the work. And so this is the ratio saying for a given weather event, can they handle most of the work themselves? That would be where if they have more internal employees, then the ratio is less than 1. If they have more external employees, the ratio is greater than 1. And you can see for both tropical storms and winter storms, there's a large role for mutual aid employees, which is one of the reasons why this pre-storm modeling is really important, because they need to identify how many people they need, and they need to make those calls early before the storm occurs in order to have them in place. So our work over the last number of years has focused on developing decision support tools, models, for pre-storm preparation. This has been both for electrical utilities and also for state and federal emergency management agencies, and to also inform long-term hardening and mitigation. So there's two ways really these models can be used. One is to say what's going to happen tomorrow or Sunday or Monday, and how bad is it going to be, and how many people do we need to repair that damage? So that's that short-term pre-storm preparation. The second way these models can be used is to say if tropical cyclone frequency or intensity increases, or given climate change, and we think about where the electrical power grid is vulnerable and where there could be a lot of storm-related outages occurring in the future, and prioritizing those locations and doing things like replacing wooden poles with steel or concrete, changing the type of transformers. After Harvey, there was a lot of conversation in the Houston area about burying infrastructure underground. So as opposed to having overhead power lines, does it make sense? Is it cost effective? Will it help harden the system to bury lines underground? So those are the kind of things that one can use these models for in a longer term context. Today, I'll mostly focus on the pre-storm preparation, but just to show the kinds of questions here, the timescales of focus, it could be years to decades. It could be a seasonal focus, so preparing for a season in advance. How many materials or crews are we going to need for the hurricane season this year? And then on a very short time scale, hours to days ahead of event, determining where to place crews and how many crews you need. This is where the work that we do fits out in the overall emergency preparedness that all utilities have. And so they have an emergency plan, they have an organization, they track weather, they have a command center operations and communication and logistics and all of these things. And so the storm modeling that we do is just one piece of a very involved decision-making picture that utilities and emergency management agencies are involved in. But this is a place where we think there can be tremendous room for improvement by providing more accurate, timely, and customized predictions of how weather is likely to impact their operations. When we're thinking about something like a hurricane, this is kind of the normal lead time for a hurricane, that something like 4 to 6 days before landfall, utilities need to determine how many crews they're going to need and start to think about and prepare and mobilize. In the days, a few days before landfall, they need to adjust then those mutual aid requests and also allocate where those crews are going to be positioned, and to think about restoration priorities. So what parts are going to be hardest hit for their system and which parts will they restore first? These are often critical infrastructure. Things like hospitals have a higher priority than residential neighborhoods. And then after a storm, obviously during the storm making landfall, it's shelter in place, make sure your crews are safe. And then after the storm passes, optimizing and managing the restoration process to try and get everyone back as quickly as possible. So this pre-storm modeling that we're doing is a critical part of the process because it influences, it makes sure. In fact, we got into this because a utility got caught. We won't name the utility, but there was a major hurricane that affected their service territory. They were not fully prepared. They hadn't requested enough crews. It took them a very long time to restore power. And the Public Utility Commission then mandated that they must implement a model, and they must utilize those models to improve their pre-storm forecasting so that they don't repeat that situation in the future. And so how many mutual aid employees are we typically talking about? Here again is data from our benchmark study of major utilities in the United States, that often for hurricanes or tropical storms, they're requesting something like 1,500 additional employees to help respond to those events. And in some cases, those employees can come from really far away, depending on how big the event is and where it occurs, including borrowing crews from Hydro Quebec or from places that are well removed from where the storms are occurring. And you can see similarly with winter storms and ice storms, there's also a very large number of mutual aid employees. This is an expensive proposition. You're often paying these employees double overtime. You have to pay for their travel and meals and accommodations. And so these are millions of dollars per day type decisions, depending on how many crews you are bringing in. So how do we do our modeling? There's two basic approaches. One is that we could take would be based on fragility. So an engineering component level analysis, looking at the probability of failure of an individual structure. So like what is the probability that a pole fails when exposed to a 60-mile-per-hour wind, 70-mile-per-hour wind, 100-mile-per-hour wind, and then based on the rolling up those component level estimates to come up with an overall system estimate of the damage from a storm. And so within the engineering literature, there's lots of examples of where this has been applied. An alternative approach is a statistical or machine learning approach, where we're now aggregating information over some kind of spatial area and then training models based on past storm events and making predictions for the future storm events. And each has advantages and disadvantages. There's no single best approach for all cases. It kind of depends on what situation and what you're trying to do. In general, though, the machine learning approaches have strong predictive accuracy, and this is the place that I'll describe today, our work with statistical and machine learning methods. These provide area-based estimates, and they incorporate a very large number of potential variables, not only just a single meteorological impact like ice loading or wind speed, but hundreds of variables The challenge in this case, though, is that we need good training data set, that the model performance is heavily dependent on our historical data. So in our case, we use machine learning and data analytics approaches because of the volume of data. So this shows an example of the number of assets, the number of individual components within an electric utility. This one is one of the utilities that we worked with in California. And so in our models, we account for the location of every pole, every transformer, the age of those assets, the loading of those assets, and to attempt to appropriately measure the vulnerability of the system to a particular weather event. So for one operating company, we might have 10 or more gigabytes of data on the different variables that we're trying to represent. So data volume is one reason, data variety. So we incorporate, as a geographer, I incorporate not only the meteorological components, but a lot of other environmental and topographic and land cover data to, again, attempt to represent how a given wind speed might vary depending on the elevation or aspect or slope in a given location, or the land cover. Is this a forested region, or is this a residential area? Many of these relationships are nonlinear. So here we're showing partial dependence plots for an order volume model that we developed for a particular utility that focuses on winter. So as what this shows is that as the amount of snow increases, the number of orders, you can think about this as the number of things that break that they have to send a crew out to. So the number of broken poles or number of downed lines. And so these are not simple linear relationships with most of these variables. Therefore, using machine learning is more flexible and can accommodate that. Finally, when we're dealing with problems like power infrastructure modeling, the most common impact from weather is no impact, that blue sky days dominate the data set, and that in most times in most locations, we have no weather-related outages or damage occurring. This is what's referred to as a zero inflated data set. So we're really interested in the tails of the distribution, the really extreme events, but those really extreme events are very rare. And that's another reason why machine learning approaches are we found to be the best in our work. So let's move to a particular example. All of that was just to set up the kind of general scope and focus of our work. We've done this type of modeling for a large number of utilities in the United States. We've worked with an international utility. We've also done this work for the Department of Energy through Grid Modernization Lab Call in cooperation with Los Alamos, looking at tropical cyclone and hurricane impacts and doing power outage modeling. I don't have time to talk about all of those applications today, so I selected one utility to present as an example of how this works. So typically when we're developing a model for a utility, the first thing that we do is generate a database that includes all of the system assets. So where are their poles and transformers? What type are they? When were they installed? All of that information. Historical impacts in terms of outages and damages to their system. Historical weather conditions, so what weather conditions caused those damages. Geographic and environmental information like land cover and slope and topography. And other things. If we're doing a resource model, we need to know how many crews did they use for past storms. That's used to train a model. And once we have trained and validated a model, then we can make it operational by driving the model with weather forecasts. And often we forecast a variety of different things because we need to give the decision makers the right information at the right time. So if they're thinking about crews and restoration, the number of crews that they need is determined by the type of damage and the amount of damage that they have. However, from a PR perspective, often the number that gets reported in the media is not how many damaged poles you have, but how many hundreds of thousands or millions of customers are out. And the number of customers are out also drives things like their call volume and how much scrutiny they're getting from politicians and the Public Utility Commission. And so we also do customers interrupted and outage models. And then finally, for some utilities, we develop models that predict how many line crews do they need, how many vegetation crews, how many hours of personnel time will it require to restore damage from this kind of storm. So here's an example for one of the utilities that we work with showing, and you're not meant to read this, I can't read it on my own computer screen, but this shows you the types of data that we use to build our models. And so we have things like all of these different asset categories, we have damage attributes, we have environmental data related to land cover and soil conditions, we have then the weather variables that we use. And so in this one case, there are more than 300 variables used potentially as potential predictor variables. We have to go through a variable selection process to come up with our final model, our most parsimonious model. And this generates a large data volume because we have this information over hopefully a 5 or 10 year period to train and validate our models. So for AEP, we're running these at district level. So this is a unit that they use for internal organization within their company. A typical district spans a number of counties. We provide these predictions daily. So for example, we're predicting damage for today and for the next 3 days. Currently, we're using calendar days, and then we're updating it every 6 hours when a new weather forecast comes out. And in this particular case, we're forecasting the expected number of customers interrupted in each district, the expected damage in poles, transformers, both overhead and underground transformers, and spans of line and underground cables. So those are the things that we're predicting operationally. So a note, as you might have expected with 300 plus variables, and it is very possible to overfit a model. And so we are not interested in the in-sample performance or how closely we can predict events that we're training on. We're very concerned with out-of-sample validation. And so there's this traditional curve of bias variance trade-off, and so that there's an optimum level of model complexity. So we're trying to find that optimum level of model complexity, and we're trying to find that by doing extensive holdouts, lots and lots of holdouts. And the only thing that matters to us is how well the model does on storms it's never seen before. And so we do random holdouts, we do operating company-based holdouts, we hold out a single storm, Hurricane Laura, and then predict for Laura based on the other storms, holding out one day or one location or one operating company and predicting based on the others. And so this is a critical part and an iterative part of the model development. So for AEP, we're running models for all 8 of their operating companies, and this is currently used for pre-storm preparation and also in terms of customer-facing communications. So they want to be proactive about providing customers with information before a storm occurs. So let's look at an example to make this a little bit more tangible. And I picked a couple of recent examples because these models are running operationally. We have lots of storms to choose from, and 2020 is nothing if not exciting from many standpoints. And one of them is the level of tropical activity that's occurring. So we'll look at the impacts of Hurricane Hannah. Hurricane Hannah made landfall in Texas on July 25th, 26th time period. This is based on the operational predictions that we were providing in advance of the storm. So for this particular utility, they have a dashboard that they can use that looks like this. We're providing forecasts based on the global forecast system. So that's the numerical weather model that is driving our predictions. And an important note there is, depending on which numerical weather prediction model you use, you're going to get a different answer. And so this is why I mentioned this. Also, that the track and forecast that GFS thinks Hannah's going to take might be different than what the National Hurricane Center or other numerical weather prediction models indicate. So we want to provide as early a prediction as possible. And so this is what our predictions of wind speeds. I'm just focused on maximum wind gusts for the districts in Texas that we're running this model for. This is what the forecasts look like at 0Z on July 22nd, valid for July 25th and 26th. And so what you can see if you look at these wind speeds, high 20s to low 30 mile per hour. So this would not result in much damage in this area. And the main reason is because at this time, the storm was expected to make landfall around Corpus Christi, or a little north of, a little east of Corpus Christi. And therefore, it was expected to be quite weak once it reached the AEP service territory. And so our earliest forecast says, hey, Hannah's not going to be much of an issue. And you'll note at this point on Wednesday, I pulled off the NHC map that corresponds roughly to this time. And so at this point, it was not yet a named storm. This was Tropical Depression 8 when we provided our first prediction. Here's the 23rd, so 24 hours later. And again, you can compare the wind speeds here and see that they haven't increased that much. And in fact, if we look at what the model's predicting, the model predicts a median of 21,000 customers interrupted and the 90th percentile of 71,000 customers. And we have the number of customers interrupted for each district shown here based on these different percentiles. So one of the things to note is, because of the uncertainty in our models, we provide probabilistic predictions. A single point estimate, although desirable from the decision maker standpoint, is not very useful or appropriate given all the uncertainty, given the uncertainty in the weather forecast, in the form and fit of the model, and all of the other things that are going on. And you'll note that even on the 23rd, AEP Texas was not expecting to see a major impact from this storm. The green here is what actually occurred. By the 24th, we see a large change. So between the 23rd, where the 75th percentile is saying 45,000 customers out, on the 24th, it's now up to 208,000. So this is a significant jump in prediction. And you can see why. Now there's been a shift in the track of the storm and an intensification. So now we're expecting maximum wind gusts between 60 and 70 miles per hour. And the location of where the maximum number of customers interrupted has shifted to the Rio Grande Valley. And so that is a big change from what we saw the day before. And just as a note here, for most of these storms, the operational guidance that we give to our utility partners is that our probabilistic models are most accurate. If you want a point estimate, often you would use the mean or median, but in storm outage modeling these models are quantile random forest models. And so the upper quantiles here, so the 75th or 90th, are best estimates of major storm damage, because the models tend to systematically underpredict because there's so few large events upon which they're trained. So we would say for this event, our best estimate was the 75th. If they were going to look at a single number, that was the number to look at. So then on the 25th, you can see that now the track has really shifted to the south and the storm is intensified. So we have maximum wind speeds expected upwards of 70 miles per hour, and the number of customers without power has jumped to 234,000. This shows the GFS forecast maximum wind gusts. So the question is, how well did the model do? One way we can validate the model is by looking at GFS wind forecast versus observed. And we haven't gone back and done a more detailed analysis. So here we're just showing the polygons from the National Hurricane Center of tropical storm force and hurricane force wind swaths. Qualitatively, these match up reasonably well. More important to the utility is how does the prediction validate against what they experience. And so here are the district level customers interrupted, and here are the 75th percentile predictions. And so we can see that we underestimated in Corpus Christi, overestimated in Laredo, underestimated in Rio Grande. But overall, the order, the districts that were expected to receive the most impacts received the most impacts. So rank order, the model is relatively correct. In order of magnitude, the model is relatively correct. And if we include not only this particular storm, Hannah, from July 25th and 26th, but if we look at the validation for all days in the month of July, our model had a relatively high correlation with the observed. The bias is less than 1, so it means there's a little bit of a systematic underprediction, and the error is around 7,000 customers per day as being the mean absolute error. So this is not a perfect model, but a useful model in terms of their decision-making process. So there's been other hurricanes. Even more recently, we can look at the impacts of Hurricane Laura. So now we're switching to a different operating company within AEP. And so SWEPCO serves parts of northwestern Louisiana and northeastern Texas, and that's the districts that are shown here. This is our prediction, our forecast from August 27th, when the storm was approximately here. And obviously, when it comes to Laura, we don't have all the data yet. So we get data delivered to us roughly a month after. So we're waiting for the official number. So I don't have an official validation for you for Laura. But again, just to provide an example, here's the forecast from our portal on the 27th of August. And this is showing the 95th percentile. The 95th percentile was around 122,000 customers interrupted. The median was much below that, but you'll note that the maximum expected wind speed in the study area was quite high, upwards of 85 miles per hour, and a lot of rain forecast to occur. And so both of these suggest that the median would substantially underestimate what would occur. If we pull data off, so this is the actuals against which we can, our preliminary validation. So this is probably an underestimate of the total magnitude. This is just one operating company that we deal with in this region from after the storm had mostly passed through that area. And it was around 118,000. So again, not a perfect prediction, but one that is in at least the right order of magnitude. Now, we do not work with Entergy, but another utility that serves Louisiana is Entergy. And I pulled this off this morning from poweroutage.us. So this shows, even though we're talking about a storm that made landfall on August 27th, today on September 11th, there are still upwards of 100,000 outages in the state of Louisiana, and many of those, about 70,000, are Entergy's in Entergy service territory. And they put out this infographic that I thought was really revealing. So they report 971 transmission structures damaged or destroyed. These are these 500 kV huge steel structures that were destroyed by Laura. In addition to, so lots of transmission outages and lots of distribution outages. So 6,500 distribution poles damaged, and 333 miles of distribution line down. So this is, likely still a number of weeks away from full restoration, and just a catastrophic event for obviously the state of Louisiana and especially the Lake Charles area. So now we've showed an example of how the models are used. Now let's turn to some of the challenges with modeling in the couple minutes that remain. There are a lot of sources of uncertainty when it comes to making these predictions. Predictions are hard, especially about the future, and all models are wrong, some are useful. You know, those are two things that modelers often talk about, and those are both absolutely true here when it comes to modeling the impacts of weather on electrical infrastructure. First and foremost, the largest source of uncertainty is in the weather forecasts themselves. So we saw with Hurricane Laura, as the track shifted, obviously that changed greatly the expected impacts for AEP Texas. And so our predictions are conditioned on usually a particular weather forecast. And so that's one place where there is substantial uncertainty, especially as the track and intensity of storms changes prior to when they occur. The second is uncertainty in the other inputs to the models. And so the system itself is always changing over time. If we think about Entergy, they are going to be basically rebuilding from scratch a huge part of their system. And so predictions made for future storms in Louisiana for Entergy, if they're conditioned on what the network was like in the past, are going to systematically likely over-predict damage because the system will be new and improved once it's completed. Finally, there's uncertainty associated with the form and the fit of the model itself. And we look at a lot of different models, and depending on what type of model you use, you get a different answer. Finally, the spatial and temporal resolution of predictions. So we talk a lot about these kinds of issues related to scale and modifiable unit area problem in geography. And so this is a place where we can see examples of how that plays out. So let's show what this looks like. Here are two examples. These are kind of the spaghetti plots that you commonly see. So each line here represents a prediction from of the same hurricane from a different model. And the spread of these tracks indicates something about the forecast uncertainty. And so in this case, interestingly, we have two examples from the same hurricane. So Hurricane Gustav on August 25th, shown on the left, and from August 29th, shown on the right. And obviously the one on the left, there's significant uncertainty in track. And the one on the right, there's much more confidence or agreement amongst the models in terms of the track. And so we want to be able to capture some of that in our predictions. One way we can do that is using this Monte Carlo wind speed probability model, which generates 1,000 forecast realizations. So that's how the National Hurricane Center, for example, generates these maps that show the probability of hurricane force winds given the current track and intensity of a tropical storm. And so we've leveraged this previously. So rather than running our models for a single track, we ran them for all 1,000 tracks and produced a prediction, in this case, based on Hurricane Katrina, focused on a utility in Alabama. And so if we just use the National Hurricane Center best track, that would give us a prediction of about 7,000 outages here. These are not customers, but outages. And a single outage could be thousands of customers versus the actual number of outages, which is 10,000. And if we use the ensemble average at least gets us closer to what the actual was. It also helps us think something about the worst case scenario. So how bad could it possibly be, or the best case scenario for Hurricane Katrina. And this particular prediction is just 24 hours before landfall. Another way we can represent uncertainty, as I mentioned, we use quantile random forests. So we're predicting the quantiles And therefore we can get this shading. So the blue line, which you might not be able to see here, is the median model prediction. The red shading represents the 25th to 75th percentile range. So this is our uncertainty around our best estimate. And then the black is the actuals. And so you can see that for some events, the black dots are significantly above or significantly below where the blue line is, but the uncertainty bands are pretty good at capturing the actual number of outages that occur. Another source of uncertainty is the type of model. I don't have time to talk about this in detail, but just to say that there's a lot of different models that we evaluate. And so most of these are multi-stage models, and many of them are either we are resampling or using part of the distribution or bootstrapping the data that we have to come up with a more appropriate model. And here we're showing both the performance in terms of mean absolute error if we use a point estimate prediction, or the continuous ranked probability score if we're using a probabilistic prediction. So the details of this work are in this IEEE Transactions in Power Systems paper. Spatial resolution. So as geographers, we know that these kinds of things matter, and we have done analyses to say if we're predicting power outages at this finer grid cell resolution, a 5-kilometer grid laid out over the state of Ohio, versus predicting at districts. So we could predict at grid cells and roll them up to districts, or we could predict at districts directly. And we see that in both for Ohio and Indiana, Michigan, that we get a much better prediction if we're aggregating data to a coarser spatial unit, like a district. And we've done this work. This is not unique to AEP, and it's not unique to Ohio. This also is the case for other work that's been done in for Southern Company. All right. So I will wrap it up with a few concluding thoughts and directions for future research. So first, these models are meant to support decision making. So all of the work that we've done here is in close collaboration with the electrical utilities and their storm bosses and the people who are responsible for making the pre-storm preparation decisions, that they help us learn about their data. They tell us about what they need and when they need it in the decision-making process. And so this is critical. Often in academics, we build a really cool model and then throw it over the fence and hope that someone is going to use it. It's clear to me that that would not be a winning strategy in this case, that it's necessary to have the decision makers help co-develop these products and tools all the way along in order for them to be useful for them. While I focused on electrical utilities here, this kind of work and hurricanes, this kind of work could be applied to ice storms, to wildfires, especially in California. We've seen that interaction between electrical utilities and wildfires, and many other applications. And this is an example of decision-making under deep uncertainty, that the weather forecast uncertainty, the uncertainty in the form and fit of the models, the spatial resolution, the type of model, there's so much uncertainty here. So quantifying, characterizing, and communicating under deep uncertainty is a significant challenge. So where are we headed next? One of the places that we want to focus on is applying these approaches to other real world problems, one of which the headquarters for Nationwide is here in Columbus, Ohio. And so we are talking to them about doing catastrophe modeling. So predicting the number of insurance claims and the total amount of insured losses from the same types of storms that we work with for the electrical utilities. And so that's one area. Developing new modeling approaches. So we're working on a Bayesian model averaging approach to doing this. So rather than picking a single model, combining many models together and using and optimizing the weights of each one of those members based on the previous predictions, and updating and learning those weights over time. And as I mentioned, another place is these predictions that I presented today were based on a single numerical weather prediction model, GFS, but we could also run in parallel many other numerical weather, or use the data from many other numerical weather prediction models to again try and capture some of that uncertainty based on that approach. So I will conclude there, and I am happy to take any questions that you have. I'd like to acknowledge all of the support that we've received from a variety of partners, and of course the excellent research team. I get to give the presentation, but the folks listed here and on the first slide are really the ones who did all of the work.
Well, thank you very much, Stephen. I'm sure folks at home are clapping. This was fascinating. I know it's been a few years in the making, and it's come a really long way. It's amazing how much work there was. Let me invite the audience to pose their questions. Again, look into the right-hand side of your YouTube channel. That is where you can comment in the chat box and leave your question. It may ask you to log into your personal Gmail account if you haven't already. You're welcome to do that and come back and refresh the page and pose your questions. We'll be here. We have ample time, at least 8 minutes before the top of the hour. Dr. Quiring has agreed that this talk will stay online on this YouTube channel, this very same link. So you're welcome to refer back to it if you have questions. In the meanwhile, I think, Stephen, I have a lot of questions, and I know some of my students in the spatial data science class are in this talk. And I would love to, from a geospatial science point of view, that learn a little more about the models. So the target variables seem to be, are these separate models? One is looking at the wind gust prediction, and then the other one is looking at the number of people, the population affected. And I also understood that a flavor of random forest is being used to do these predictions and output quantiles, if I understood correctly. And just wondering if that model is trained based on any utility company's historical data, or is this some sort of model that is trained on on a more generic data set, not necessarily place specific, and then might be used in other places as well. So comments on the target variables, what those are, and how the model generalizes from one place to another, if it's in fact that what you're doing.
Great. Yeah, thanks for the questions. So our target variables here include the number of customers interrupted. So a customer interrupted would be a single residential or commercial customer, basically a meter. So my house is one AEP customer. And so we have this information from their outage management system at the address level, and we can then aggregate it up to a spatial unit where we're making the predictions. And so one way that we aggregate that is to these regular grid cells that correspond to the resolution of the meteorological variables, so the numerical weather prediction model or the National Digital Forecast Database or whatever other source of meteorological data we're using. The other target variables are the number of damaged components. So we're counting up, again, the number of poles and transformers, the number of miles of line that are down, and also summing those to a spatial unit like a grid cell or a polygon or a county. And then we do that historically. So in this example, we have data from 2010 to present, and for every day, for every location, we're counting up how much damage or how many customers lost power. And we also know from using past weather information what weather conditions were observed at those locations. So In this case, it is a utility-specific data set in this application that I presented here, meaning they have to provide us with data from their OMS, and then we process that to come up with our target variables. And then you had a question about, so the wind speed is not, in this case, something that we are directly predicting. We're taking wind speed predictions either from the National Weather Service or from a particular numerical weather prediction model. The one we used in this example is the Global Forecast System. And so that model provides predictions of a whole host of meteorological variables. And we use something like 60 different meteorological variables. So we're taking output from their numerical weather prediction model as input to our power outage or power damage model.
Thank you very much. That all
Oh, and then you also had a question about generalizability.
Yes.
So in this case, this application is using historical data. So we are, for each operating company, we're treating it as a separate entity, and we're not pooling data across operating companies. And so we are trying to, by doing that, account for the unique characteristics that the power grid in Ohio might be different than the power grid in Colorado or Texas, and that there are also some unique environmental factors like the density of tree cover or the stability of the soils, or those kinds of things also vary over space. And so a 60-mile-per-hour wind gust is not going to cause the same amount of damage in each location. Therefore, it is we treat each location as a unique training data set. We've in the past done some work to see whether a model trained in one location, how well does it perform applied to a completely new location that it has not seen before. And there definitely is the ability to do that there can be some space for time kind of substitution in training the models, but it doesn't always work. And so one extreme example would be if we train a model on a place where most of the power system is overhead, where most, like in an area where there's a lot of above ground distribution poles and lines, and then we apply it to New York City. Well, how many power poles do you see in New York City? Not very many, because all of the electrical infrastructure is buried underground. And so in that case, your model would not do well in predicting damage, because a 60-mile-per-hour wind is not going to blow over any poles, because there's very few to impact.
That makes sense to me too. We are at the top of the hour. There is a few questions from the audience. I want to first thank you everyone who tuned in. Feel free to subscribe as they do on the on the YouTube board, but we'll send you advertisements for our upcoming talks. Dr. Quiring has agreed to stay on to address the audience questions, but thanks again for tuning in. Stephen, the next question comes from the audience. The nuclear power industry was recently interested in reevaluating natural hazards at current operating plants, including wind loads that consider new data captured in radar and sources. Is your research designed to reevaluate these data given climate change and changes to extreme weather patterns, including reassessing the risk? I know you alluded to the changing patterns in the future.
Right. So it is possible and useful to leverage the models that we've developed to assess how risk is changing over time. And in fact, a large number of utilities are undertaking these kinds of long-term risk assessments, where they're incorporating the potential changes in future hazards, so wind speed and return periods, hurricane frequency and intensity, and other factors that might influence their infrastructure, and to try and assess how much is risk going to change in the future, therefore what decisions should they take today. And so in some cases, this is mandated. by the Public Utility Commission in the states that those utilities are working in. The state of New York is one example where utilities are required to address that climate change component in their long-term risk assessment. And but there are also other utilities that are just proactively for trying to improve their resilience in the face of future climate change, trying to reassess, are the historical return periods that have been used for wind speeds or lightning or ice loading, are they going to be relevant in the future, and how much additional risk and where is that going to occur? So what things should they change?
Thank you. And I think this will be the last question from the audience, going back to the generalizability, how easy or difficult it would be to use similar models for different natural disasters like wildfire. I know you alluded to this in your conclusion slides too.
Yeah, so it is possible and relatively straightforward in terms of applying this to other kinds of natural disasters, other kinds of weather events, things like wildfires. The building the database, training the models, using the different machine learning approaches are really flexible, regardless of which natural disaster we're talking about. The challenge comes in that these models learn from the historical data. And so in places or for types of events that are rare, or where there's not good data collected on past impacts, then it becomes more challenging to train an accurate model. The generalization is actually easier. So in this case, we have some models that we run outside of the specific utilities for looking at hurricane impacts. And those ones we have generalized spatially. So saying we have utility specific information from this state and from this location, but if we want to run it everywhere in the United States, we can do that. The accuracy of the model decreases a little bit, but we still can do really well at predicting the impacts in locations where we don't have all of the same, like we don't know where all the poles are and we don't know the age of all the infrastructure. That kind of generalization is easier than to go from, okay, you're modeling hurricanes, to now look at wildfires or earthquake related damage to the infrastructure system. If there's not good historical data, then the machine learning approach, it's challenging because these are rare but high impact events.
Thank you very much, Stephen. The last comment is by Mark Siris, the director of the National Snow and Ice Data Center here, and he says, fascinating, with which I agree. Thanks again for making time today for this wonderful talk. Thank you to folks who tuned in. We'll hopefully see you next week, and this is the conclusion of our live stream. Have a good rest of your Friday.